Leaders and coordinators who helped keep the event happening today. Even I talk about something about infinity here, but today I've chosen a different topic. I'm going to talk about isomorphism. So let me sort of give you the definition here. As usual, the dictionary is very useful. It says isomorphism is the quality or state of being isomorphic. So better to go to the etymology here. It's from Greek, same shape. And really what we're trying to answer is one or two things the same thing here. So on the right there, you have the standard etymologists don't have becoming a coffee cup. So as a topological shape, these are the same or isomorphic. So this is about isomorphism. So what I want to do is I want to give you some examples of this. So let's do something completely different. What I'd like to do is I'd like to play a game. Okay, this is a game of just choosing numbers. It's a two-player game. So perhaps someone in this table would like to play with me? Well, maybe the whole table can play together. So the idea is we're going to take turns choosing numbers, okay? And the numbers we chose without replacement. And at any time, if one of us has some three of our numbers that add up to 15, the numbers win. So since it's my game, I'll go first, and I'm going to choose the 5, okay? So now it's your turn to go. Just say a number. 7? I heard 7, so you play 7. Okay, so let's see. It doesn't matter so much. I'll go ahead and take the 6 here. So let's remember the game here. So the rules of the game. So right now I have 6 and 5. That's 11. So if I get the 4, then I guess I'll win, right? And so what do you take? And you do. Okay, so you stop me. Now you have an 11 as well. So I've got an 8, which would be a 7. I've got a 9, which would be a 6. So I actually haven't presented any problem to you at all. You want to take the 2? Great. So you have the 9, which would be a 6. You have the 6, which would be a 9. So I guess I have to take the 9. The 4 and the 2 is a 6, yeah? So I guess I have to take the 9 in order not to lose. And now you take? You should take the 1, right? But since I'm making the moves, I'll make you take the 8 so that I win. And then I take the 1 and I win the game. Yeah, look at that. Okay, that's all cheating. Okay, well, that's not the question though. So the question here, the problem here is, have you ever played this game before just now? And well, I'm hearing some people say yes, and people I was playing with said no. And so let's just play that game again in slow motion, okay? I believe you. You have played it before. So here's the idea. So let's play this game. So what I've done here is I've drawn a magic square below. Okay, so the idea is that the numbers from 1 to 9 are arranged in this square shape. The rows and the columns all add to 15, and so do the diagonals. In fact, those are the only ways to add to 15. So now let's play the same game again. So I chose the 5 right in the middle. Let me mark that with an X. And then you chose the 7, which we'll mark with an O there. And then I took the 6, and you blocked me with the 4. And then I just took the 3, which was not a very good move. Then you took the 2, and then I took the 9, and then I cheated, and you take the 8 so that I would win with the X. So have you played that game before just now? Yeah, you had, right? In fact, the game was isomorphic to tic-tac-toe. Okay, so that's the idea. It's isomorphic. It was in disguise. It wasn't so obvious that it was tic-tac-toe, but it was. Should we do another example? Yeah, okay. So, to show you what happens with 1. So, we can put the ant however we want on the log, we have to walk, and then we're trying to maximize the total distance. You see, it's got a little parachute there. So the idea is that we're trying to maximize the total distance that the ants travel on the log before they all fall off. We give them parachutes, they don't actually hurt. And so, let's go ahead. So, with 1 ant, you can see that the total distance was 1, right? 1 unit, because it's math, not physics, 2 units. Okay, but like, for example, with 2 ants, so now I have to give you another rule. So, what happens is, with 2 ants, so the ants all move at the same speed, but 2 ants, it looks like I can get a total distance of 2. Okay, so I'm interested, though, if I have like 100 ants, so here perhaps I have 8 ants, but I'm interested, if I have 100 ants, what's the maximum total distance that all the ants can travel before they fall off the log? Does that make sense? Okay, and it starts to get hard. Like, for example, these 8 ants, like, there's going to be all sorts of crazy collisions going on, and it's hard to think about. And maybe it's possible that with like 37 ants, maybe there's some sort of like critical point where 37 ants, actually, the ants can stay on the log forever. Maybe it's infinity at that point. It's not. So this problem, as it turns out, so the animation is maybe, yeah, okay, but so this problem is isomorphic to another problem. So what's complicated here is the bouncing of the ants, right? It's complicated because you get all these crazy interactions. But what if, so here what I've done is I've tried to slow down the collisions, I've tried to emphasize this, and I've made the ants different colors. What if we just made the ants all the same color, okay? And then what you notice is that it's really the same problem as if the ants were all passing through each other. This bouncing, which is happening instantaneous, because math, not physics, right? It's the same as if the ants were all passing through each other. So the original problem, they're all close to each other. Does that make sense? Okay. I guess I'll do one more example. Yeah, okay, one more example. So sometimes it can be really hard to tell if things are the same. So on the left here, I've got 2 versions of the unknown. Okay, so this is just a circle in R3 projected down. Okay, so you can see that on the left is just a circle, and on the right there, I just put a couple twiddles in it. You can see that you can easily unravel that and get back to the circle, right? And what about that one, please? That actually turns out to be, again, the unknown, but it's totally not obvious, right? It would take you maybe a while to check that this was actually the unknown. Okay, well, okay, so checking if 2 things are the same can be a difficult process. What's even worse, though, is that sometimes it can be hard to tell if 2 things are different, even if they're obviously different to you. So here's the unknown again. Okay, that's the same picture. And here's a trefoil. Okay, so this thing is not the unknown. Maybe you could actually get it to be just an unwrapped circle, an unknown. Maybe it would be possible. Maybe it would take a really long time. Maybe it would be possible. So how can you prove that these 2 things are actually not isomorphic? They're actually different. Well, what you need is you need some sort of invariance. What you want to do is you want to write down something that doesn't change as you do your little twisty moves. Okay, and then if you can show that this invariant is different on the unknown and different on the trefoil, why don't you show that they're different knots? Does that make sense? Okay, so one such invariant is called tricoloring. So what's the idea? The idea is that for every strand, okay, what I want to do is I want to color it one of 3 colors, subject to the rule that every crossing, either all 3 colors appear or only 1 color appears. So let's color the unknown. It turns out that this doesn't matter. So as you do your twisty moves, you can check that as you move this diagram around, as you move this knot around, the number of tricolorings doesn't change. So the number of tricolorings for the unknown, that's another valid coloring. Every crossing, just 1 color appears, right? And then finally for the unknown, there's one additional one, which is what I'm allowed to use these 3 colors. And for the trefoil again, I could have all blue. And now here's where things are different. For the trefoil, I actually have another color, which is for example, this one. So at every crossing, you can see at every crossing, all 3 colors appear. Okay, so if you believe me that the number of tricolors is actually invariant under all the moves that you could possibly do, it would actually show that these are different knots. This is how you can check that things are not isomorphic. Even though it's obvious to you if you were looking at these things and build them in the real world that they're different. I actually prove that they're different. Okay, so it wasn't infinity this time, but it was isomorphism, and I guess I'll say thank you and good luck.
I'd like you guys to take a note on the screen here, the stakes for today's competition. So parents, teachers, please take note of the date, March 7th, 2026, here in Irving, Texas, for the state level competition. And then what we are all here competing for today are 7 team slots and 9 individual slots, and we'll advance from this local chapter competition to that state competition today. And so I'd like to go ahead and start our roll call. So I would encourage all of the competitors, as I call your school name, please make noise, jump around.
Perfect. Scared me a little. Ereckson Middle School? All right. So we're doing the opening ceremony in this room here, obviously. This is where all testing will take place. So thank you again for being here today.
No, it's fun.
Please get in the pizza line. Any table over 60, everybody's in.
Now for the fourth place team, coached by Catherine. Fourth place team. The coach of our third place team, James Turner. It's Ereckson Middle School.